Okay, what if I told you there's a secret weapon for a whole family of really tricky interview problems? A technique that lets you solve them in just a single pass, turning a slow, clunky solution into something absolutely lightning fast. Well, today, we're going to unlock that secret.
So here's the classic challenge. You get an array of numbers, you get a target number k, and you need to find all the continuous subarrays that add up to it. Now here's the catch. You have to be fast, like really fast, and that's exactly what we're going to do, step by step.
You'll see subarray sum problems all the time in technical interviews, and for good reason. They're designed to test if you can move beyond the obvious brute force way of thinking and find a much more elegant, much more efficient solution.
On the left, you've got the brute force method. Generate every single possible subarray, sum each one up, and check if it equals k. Sure, it works, but it's O of n squared, which is just way too slow for a typical interview. Our goal, on the right, is the prize, a linear O of n solution. One single pass. That is the secret weapon we're building today.
So, how in the world do we get there? Well, the journey starts with a simple but incredibly powerful mathematical idea called the prefix sum. This is the very first piece of our puzzle.
A prefix sum is really just a running total. That's it. As you walk through the array, you're just keeping track of the sum of all the numbers you've seen so far. And here's a key detail. We always imagine a starting sum of 0 before we've even looked at the first element. It's a simple idea, but you're going to see it has some pretty profound implications.
The best way to think about this is like the odometer in your car. Right at the start of your trip, it's at 0. And after each mile, or in our case, each number in the array, the odometer reading, which is our prefix sum, just gets updated. It's always telling you the total distance you've traveled right from the very beginning. And this right here, this leads us to the core aha moment. If you want to know the distance you traveled between 2 points on your trip, what do? Right, you just subtract the earlier odometer reading from the later one. It's the exact same logic here. The sum of any subarray is just the difference between two prefix sums. Seriously, this one equation is the key to everything.
Okay, so we've got the math down, but to make this whole thing fast, we need a way to instantly remember all those odometer readings we've already seen, and that is where our second component comes into play, the hash map.
So if the prefix sum is our odometer, the hash map is our travel diary. At every single stop, we just jot down our current odometer reading in this diary. And the absolute magic of a hash map is that we can look up any past entry in basically constant time, O1 time. It gives us a perfect, instantaneous memory.
All right, it's time. Let's combine our odometer, the prefix sum, and our diary, the hash map, to solve that original problem in one beautiful single pass.
So let's go back to that core equation. We're looking for a subarray sum that equals k. With just a little bit of algebra, that's the exact same thing as saying we're looking for a past prefix sum, an old odometer reading, that is exactly our current reading minus our target k.
And here it is, the complete algorithm. It's beautiful. First, you initialize your diary, your map, with a reading of 0. We say we've seen a sum of 0 one time because, well, an empty subarray has a sum of 0 before we even start. Then we loop. We update our odometer, our running sum. At each number, we just ask our diary, hey, how many times have I seen the value current sum minus k before? Whatever the diary says, that's how many new subarrays ending here sum to k. We add that to our result, and then finally, we log our current odometer reading in the diary before moving on to the next number. It's really that elegant.
But here's where this gets really powerful. This isn't just a one-off solution to a single problem. No, this is a flexible pattern that you can adapt to solve an entire class of subarray problems.
Just look at this table. By slightly tweaking what you store in the diary and what you check for, you can solve all kinds of different problems. To count the subarrays, you store the frequency of each sum. But to find the longest one, you store the first index where you saw that sum. And get this, to count subarrays divisible by k, you don't even store the sum, you store its remainder. It's the same core engine, just with slightly different settings. And check out this awesome bonus trick. What if you're asked to find the longest subarray with an equal number of zeros and ones? It sounds totally unrelated, right? But it's not. All you have to do is pretend every 0 is actually a negative 1. Now the problem has transformed into find the longest subarray that sums to 0. It's the same pattern, just in a clever disguise.
So, you have the pattern.
Now let's make sure you can execute it perfectly when the pressure is on. We're going to cover the key details and the common pitfalls you really want to avoid in an interview.
First things first, you have to understand the trade-off. You're getting this blazing fast O1 time complexity, which is amazing. But you're achieving that by using a little extra memory for your hash map diary, which, in the worst case, could grow to ON in size. It's a classic space for time trade-off, and believe me, it is almost always worth it.
Now, these are the mistakes people make all the time. Number 1, they forget to initialize the diary with 0 to 1. This is so crucial because without it, you'll completely miss any valid subarrays that start from the very beginning of the array. Number 2, for counting problems, you have to use a frequency map, not a set. A set will totally undercount if you have duplicate prefix sums. And finally, be super careful with the modulo operator on negative numbers. In some languages, it can give you a negative result, so you should always normalize your remainders to be positive.
So when should you immediately reach for this secret weapon? The biggest, clearest signal is when the array contains negative numbers. Other techniques, like the sliding window, completely fall apart with negatives because the sum doesn't just grow. This prefix sum pattern, on the other hand, handles negatives perfectly.
All right, let's recap the most critical points you need to remember. 1. Subarray sums are just differences of prefix sums. That's the core math. 2. Hash maps give you that instant memory you need for a one-pass solution. 3. Always start your map with that 0-1 entry. And 4. Remember to adapt what you store on the map based on whether you're counting or finding a maximum length or something else.
So, there you have it. You've just added an incredibly powerful and flexible pattern to your problem-solving toolkit. The next time you see a problem about subarray sums, you'll know exactly where to start. So the only question left is, what other problems out there are secretly just a prefix sum problem in disguise?